In the last lecture, we were discussing separation of variables for a non-axisymmetric temperature field. Okay. Del square T equals 0. Okay. 1 by r square partial by partial r square partial T by partial r plus 1 by r square sine theta T is equal to f of r g of theta h of phi. Substitute into the equation and divide throughout by f g h, okay, and I will get 1 over f r square d by dr of r square. I should use total derivatives here because f is only a function of r. Plus 1 by g r square sine theta d by d theta of sine theta dg by d theta plus 1 over r square sine square theta into h d square h by d phi square. This is equal to 0. This is what you get when you substitute the temperature is equal to f of r g of theta h of phi, divide throughout by f g h. Okay. I can get into separable variable form by multiplying throughout by r square sine square theta. Okay. So, I will multiply r square sine square theta, okay, on the first two terms and just cancel out the r square sine square theta on this the third term here. Okay. 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 The first term on the left is only a function of r and theta. Second term on the left is only a function of phi, therefore, both of these have to be constants. Okay. First term is only a function of r and theta, second term is only a function of phi, both of these have to be constants. The phi dependent term 1 over h d square h by d phi square is equal to a constant. That constant has to be equal to minus m square, where m is an integer. Okay, where m is an integer. Okay. The reason for that is that only then will I get h is equal to e power I m phi, okay, for minus infinity less than or equal to m, okay, for integer m. Okay. From the requirement that at a particular position r and angle theta, okay, if I increment phi, okay, phi, note phi is the angle around the axis, okay, phi is the meridional angle, the angle that goes around the axis. If this angle around the axis goes around and comes back to the same location, it is the same physical point in space. Okay. That means that, okay, same physical point in space is phi as well as phi plus 2 pi, phi plus 4 pi, etc. Okay. So, you can always increment phi by 2 n pi, where n is an integer. You will go n times around the axis and return to the same physical point in space. Okay. Therefore, h of phi plus 2 n pi has got to be equal to h of phi. Okay. That requirement means that m has to be an integer, and it can go from minus infinity to less than equal to infinity. Okay. So that was the separation of variables solution in the phi direction. Okay. Alternatively, this can also be written as h is equal to a cos m phi plus b sine of m phi. Okay. But we will write it using complex variables in this case. Okay. And the orthogonality relation, so this is h m. Okay. For a particular value of m, you get e power I m phi. The general solution contains all values of m in general, okay, because any value of m satisfies this condition, this periodicity, the periodicity condition that when you go around by an angle 2 pi, you return to the same physical location in space. Okay. Now, the other solution, okay, the other part of the equation. So, this is equal to minus m square, that means that this has got to be equal to m square. Okay. So, therefore, I have r square sine square theta into 1 over f r square d by dr of r square df by dr plus 1 over g r square sine theta d by d theta of sine theta dg by d theta, okay, is equal to m square. Okay. This r square can be cancelled out on both sides, okay, on the left side, and I can divide throughout by sine square theta. Okay, divide throughout by sine square theta, and I will get 1 over f d by dr of r square df by dr, okay, plus 1 over g sine theta minus m square square theta. This is equal to 0. Okay. The first term is only a function of r, the other two terms are only a function of theta. Therefore, both have to be constants. Let us look at the theta equation once again. Okay. Okay. I am getting 1 by sine theta d by d theta of sine theta dg by d theta okay, minus m square g by sine square theta is equal to 0. That is, I have multiplied these blue terms by g. Okay. So, I multiplied throughout by g and this is the equation that I get. This is not equal to 0, it is equal to some constant alpha. Okay. Alternatively, I can express cos theta is equal to psi, which means that d psi is equal to minus sine theta d theta. Okay. And expressed in this form, as we had done earlier in the Legendre polynomial case, I will get d by d psi of sine square theta dg by d psi, okay, minus m square g by sine square theta is equal to alpha. Okay. And since cos theta is psi, sine square theta is 1 minus psi square. Okay. So, I will get So, this is the equation that we get in the theta direction. Okay. This is the equation that we get in the theta direction. Note that when we had solved for the axisymmetric case, for the spherical inclusion in a matrix subjected to a linear temperature field, we had got almost the same equation. We had got d by d psi of 1 minus psi square dg by d psi. Okay. This is equal to alpha. In that case, m was equal to 0. There was no dependence on the phi direction. Okay. And we had found that the solution for g is finite at theta is equal to 0 and theta is equal to pi. Okay. The solution for g is finite at theta is equal to 0 or theta is equal to pi only if this alpha is equal to minus of n into n plus 1, where n is an integer. Okay, where n is an integer. So, the solution was finite only if this eigenvalue was minus of n into n plus 1, where n is an integer. Okay, where n is an integer. Okay. This equation is slightly different because it has this additional form. Okay. So, to find out the condition, you have to go through the series solution once again. Okay. That series solution is complicated because I have a 1 minus I square in the denominator here. Okay. I have a 1 minus I square in the denominator here, but nevertheless, if you go through the series solution, you will find that you have finite solutions for g at xi is equal to plus or minus 1 or at theta is equal to 0 and pi, once again only if n is an integer minus n into n plus 1. Okay. Okay. So, the condition is that n is an integer and n has to be greater than or equal to the magnitude of m. Okay. Note that I said n is m goes from minus infinity to plus infinity. It can have any integer value. Okay. For any integer value of m, if you go around by an angle 2 pi, you will come to the same point in space. Okay. I should note here that this is actually a positive integer, because n was equal to 0, 1, 2, etc. Okay. So, this is also valid only if n is a positive integer and if n is greater than or equal to m. Okay. So, for a given n value, the m value can take values from minus n to plus n. Okay. Only then is the solution finite at theta is equal to 0, at theta is equal to pi. Okay. And the solutions for this are once again Legendre polynomials. Okay. The solutions for this are once again Legendre polynomials. Okay. G is equal to p n m of cos theta. Okay. What we had got earlier was for m is equal to 0. So, p1 was basically p1 0, p2 was p2 0 and so on. Okay. So, in that case n was an integer and m was equal to 0. This is the more general case where you have p n m of cos theta. Okay. And the orthogonality relation for this, the orthogonality relation for this, note that the orthogonality relation for m was of the form integral d phi between 0 to 2 pi h m of phi h n star of phi. Since it is complex, you have to multiply it by the complex conjugate. Okay. Okay. The complex conjugate of e power I n phi, the complex conjugate of e power I n phi is equal to e power minus I n phi. Okay. So, this is also the same as integral 0 to 2 pi d phi h m of phi h minus n of phi. Okay. this is equal to 2 pi times delta m n. Okay. Let me write this slightly differently so that we can use it, okay, in our orthogonality relation. Okay. I will write this as h m prime. Okay. This is minus h m prime. This is delta of m m prime. Okay. So, h m of phi times the complex conjugate of h m prime of phi integrated over phi from 0 to 2 pi. Okay. It is non-zero only when m is the same as m prime. Okay. Note that when we do the orthogonality relations for complex numbers, we have to take the complex conjugate. Okay. For this, okay, for this g p n m of cos theta, okay, for this g which is p n m of cos theta, the orthogonality relation is of the form integral 0 to, or rather of psi. Okay. The orthogonality relation expressed in terms of psi is, okay, integral minus 1 to 1 d psi, okay, of p n m of psi p n prime m of psi. Okay. Note that the index is m is the same on both of these. Okay. N is changing. Okay. N is different in both of these. Okay. This in terms of theta, this can also be written as integral 0 to 2 pi sin theta d theta p n m of cos theta p n prime m of cos theta. Okay. This is non-zero only if n and n prime are the same, delta n n prime, into a normalization factor 2 into n plus m whole factorial by 2n plus 1 into n minus m whole factorial. Okay. So, this whole thing times delta n n prime. Okay. Okay. So, this is non-zero only when n is equal to n prime. Okay. And when n is equal to n prime, this integral depends, as you can see, okay, both on n and on m. Okay. This integral depends both on n and on n m. Okay. So, therefore, this is the orthogonality relation for the theta direction, okay, where p n m is the solution of, okay, okay, p n m is the solution of this equation, okay, this equation such as just as p n was the solution of this Legendre equation with m is equal to 0. Okay. So, this is the solution. So, this term is minus n into n plus 1. Okay, this term is minus n into n plus 1. That is what we had just solved. Therefore, this term is n into n plus 1. Okay. This term is plus n into n plus 1. Okay. In the r direction, 1 over f, okay, d by dr of r square df by dr is equal to n into n plus 1. D square f by dr square plus 2, sorry, okay. I can multiply first throughout by f, okay, multiply throughout by f, and I will just get an f on the right side. Okay. This becomes r square d square f by dr square plus 2r df by dr minus n into n plus 1 f. This is equal to 0 in the r direction. Okay. So, this is the solution in the radial direction. we had already solved this when we did the Legendre polynomial expansion for an axisymmetric problem, and f turns out to be equal to a, okay, r power n plus b by r power n plus 1. Okay. The growing harmonics increases proportional to r, decaying harmonic decreases proportional to 1 over r power n plus 1. Okay. So, that is the solution for f. This is the solution for f. Solution for the g in terms of theta, and this is the solution for h. Okay. The most general solution, okay, for the temperature field T, okay, is equal to a r power n plus b by r power n plus 1 p n m of cos theta into e power I m phi. Okay. Now, there is a summation over both n and m. Okay. There is a summation over both n and m. Okay. There is summation. Okay. N of course can go from 0 to infinity. Okay. N of course can go from 0 to infinity. However, for m we had the condition. Okay. We had the condition that for the series to be finite, we required that n has to be greater than or equal to m. Okay. Okay. For the series to be finite, we required that n had to be greater than or equal to m. Okay. So, therefore, m can only go from minus n to plus n. Okay. M can only go from minus n to plus n. Okay. These coefficients, these constants are functions of two coefficients. Okay. These are functions of two coefficients. Okay. A n m, p n m. Okay. So, it is of the form a n m times r power n plus b n m by r power n plus 1 p n of m of cos theta times e power I m phi. Okay. So, that is the spherical harmonic expansion. Okay. So, that is the general spherical harmonic expansion. Okay. You can see that it has the same form except that it has this additional term which now depends upon phi. Okay. These two terms put together, okay, these two terms put together have the theta and phi contributions. Okay, have the theta and phi contributions. Okay, the contributions in terms of the azimuthal angle and the meridional angle. Okay, so these two terms put together have the contributions in terms of the azimuthal angle and the meridional angle. Okay, okay, these can also be written in terms of what is called the spherical harmonics. Okay, this can also be written in terms of the spherical harmonics. Okay. So, I can also write this as T is equal to, okay, I can define, okay, y n m of theta phi is equal to some constant, normalization constant times p n m of cos theta times e power I m phi. Okay. These are spherical harmonic expansion where I separate out the radial component and the component that depends upon theta and phi. Okay. Okay. So, y n m of theta and phi, okay, is equal to some normalization constant times p n m of cos theta times e power I m phi. And this normalization constant is chosen such that the spherical harmonics, okay, satisfy orthonormality condition, that is the integral turns out to be equal to 1. Okay. So, the condition is that d phi between 0 and 2 pi integral sin theta d theta between 0 and pi, okay, times y n m of theta phi y n prime m prime of theta phi. When we are dealing with complex numbers, the second term has to have a complex conjugate in it. Okay, the second term has to have a complex conjugate in it. Okay. Since the complex conjugate of y m is equal to y minus m, this can also be written as integral 0 to 2 pi d phi integral 0 to pi sin theta d theta y n m of theta phi y n prime minus m prime of theta phi. Okay. This is equal to delta n n prime delta m m prime. Okay. So, these things, the normalization constant is chosen such that the orthogonality relation between the spherical harmonics is 1 if n is equal to n prime and m is equal to m prime, and it is 0 otherwise. Okay. So, that is, these are the spherical harmonic expansions. Okay. And in order to get this, in order to get this orthonormality, the normalization constant has to be defined as root of 2n plus 1 by 4 pi, okay, into n minus m whole factorial by n plus m whole factorial. Okay. And when expressed in terms of this, okay, when expressed in terms of this, okay, you will get that the temperature field is equal to sigma a n m r power n plus b n m by r power n plus 1, okay, y n m of theta n phi. Okay. Summation n is equal to 1 to infinity, m is equal to minus n 2 plus n. Okay. So, that is the final solution for the temperature field for a non-axisymmetric system. Okay. Now, what does this mean? Okay, what does this temperature field mean? What do all these terms mean for n is equal to 0, n is equal to 1 and so on? We already saw that for m is equal to 0, it is axisymmetric. What about the others? Okay, what does the temperature field for these other spherical harmonic expansions, what do they mean? Okay. I will try to give you a physical explanation for the meaning of the temperature fields due to each of these terms for n and for m. I will continue that in the next lecture. Okay. So far what we have done is that we have solved the Laplace equation using separation of variables. We got 3 functions, one in phi, one in theta and one in r. Homogeneous boundary conditions, effectively the periodicity condition in phi. Temperature at phi plus 2 pi has to be the same as temperature at phi because it is the same physical point in space. Okay, we got integer m. Then from the Bessel equation, from the Legendre equation, okay, for non-axisymmetric case, we got the integer n, and then we got the solution in terms of r power n and 1 over r power n plus 1. What do these physically mean? I will continue that discussion in the next lecture. I will see you then.